Hello, today we're going to be continuing looking at vectors and some kind of applications of the dot product. So the first thing we're going to do is just kind of take it pretty simple. And in example one, we want to find two vectors in opposite directions that are orthogonal to you when you use the vector 2, 5. So first let's think about what it means to be orthogonal. What does it mean to be orthogonal? Well, hopefully you remember that means that it's going to be perpendicular. Okay, and one thing that we mentioned about perpendicular vectors, so orthogonal vectors, is that they have a specific dot product, okay? So let's say that this other vector, let's just pretend that this is vector v, that's v sub 1, v sub 2, okay? What would have to happen if I dot vector u and vector v and they're orthogonal? That's right, it has to be 0. So I'm going to have that equal to 0. So what that means is that if I'm taking the dot product, that means that if I take 2 times whatever v1 is, and then add 5 times whatever v2 is, that we want that to be 0. So we want to think about something that could make that true. Now sometimes my kids will say, well, 0. Well, the issue is that the direction of the vector 0, 0 is 0. So it doesn't have a direction, right? So we can't find two vectors that are in opposite directions. We're going to have to use some numbers other than 0. So again, the goal is to create these so that they're opposites. And so one example that sometimes my kiddos will come up with right away is if we make this, for example, 5 and this 2. Now right now that means we have 10 and 10, but that just means that we just make one of them negative. So that would be 10 plus negative 10, and that would work. That would give me 0. So that's the second thing, is let's name these vectors. I'm going to call this vector v, and that's going to be 5, negative 2. And now let's make one in the opposite direction. Well, let's just switch up the signs. Let's do negative 5, positive 2, okay? This is just one of many answers, okay? There are lots of possible answers. But those are usually the kind of the simplest ones, okay? What we're really going to get into today is the idea of vector components. We've seen applications where two vectors are added together to make a resultant vector, and many applications in physics and engineering want us to do the reverse. They want us to take one vector and decompose it into the sum of two vector components. So this is kind of where we're heading. Consider a boat on an inclined ramp, okay? So we have this ramp that our boat is sitting on, okay? And it says the weight of the boat, which is the force of gravity F, is working on the boat in two ways, okay? So the force of gravity F is pulling this boat. It's having the weight of the boat, and it's pushing that straight down, okay? That's that vector F. Well, that vector F is really broken up into two different components. One thing that's happening is that it's pulling it down the ramp this way, which is this W1. And it's also pushing against the ramp, and that's my W2. Again, that's the normal force. The normal force is going to be orthogonal to that. Now, I know what happens is that to create that, we're going to take W1 plus W2. Well, we know that when we add vectors, we're going to start at W1, and then on the end of W1, we can draw W2. And then our resultant vector starts where W1 began and then W2 ended, okay? So we can see that those are two forces, and you guys, these are orthogonal to each other, which means that they are going to be perpendicular. So we have these two orthogonal forces, W1 and W2, and we call those the vector components of F, okay? So our vector F is going to be W1 plus W2. Now, just kind of a little fun fact, if F is W1 plus W2, then what would W1 be? we'll just play around with this and isolate W1. We could subtract W2 from both sides, and we could say that that's F minus W2. We can do the same thing if we wanted to know what W2 was. We can isolate W2 by subtracting W1 from both sides, and we can say that W2 is going to be that vector F minus vector W1, okay? So just kind of different ways that we could rewrite that. So what we're going to do is we're going to take the single vector in these story problems, that single gravity vector, and find its orthogonal components. So before we do that, we're going to kind of talk about any non-zero vectors u and v, okay? U is going to be made up of orthogonal components W1 and W2. So what we kind of need is we kind of need like a baseline for this. So I'm going to just draw, to try to demonstrate things, a horizontal line here. Okay, and I'm just going to call this vector v. Okay, so that u is going to be made up of two orthogonal components. One of them is going to be either parallel to or a scalar multiple of v, and that's what W1 is, okay? So vector W1 could be parallel to v, but oftentimes what it is it's just a scalar multiple. And the nice thing about a scalar multiple is that it has the same direction as that, well, it has the same look as that at that vector, but it can be made bigger or smaller or go the other way, that kind of a thing. Okay. And then we also have this W2 as a vector. And we can see that when we look at W1 and W2, that those are going to be orthogonal to each other. Sometimes when I have trouble visualizing it, what I'll do is I'll start at U and I'll try to like drop the perpendicular to the vector V that we're trying to land on, and then complete the right triangle, because that's really what we're making here. We're just making these little right triangles to find W1, and then I'm just cautious with that direction. Okay, so notice if we take W1 plus W2, we have this vector U that we're dealing with. Okay, and again, U is made up of these orthogonal components, W1 and W2. And again, those are called vector components. Now here I made mine horizontal and vertical. They don't have to be horizontal and vertical, but I drew my V as a horizontal, so that's why they ended up that way. Okay. Again, W1 is going to be the vector component of U that is parallel to, but usually we're going to think about it in our applications as a scalar multiple of V. And what we call this is we say that W1 is called the projection of U onto V. And when we're looking at the idea of projection, what we notice is that, like, I like thinking about it like if you were to shine a light on U, what would the shadow of U look like on this specific vector V? Okay, so I know this isn't the same direction, but it's kind of like this idea. This is like a light shining to see where the shadow lies. This vector here is our vector V. This is our vector U. We're shining the flashlight and projecting vector U onto vector V. And that's what we get right here. And this piece is our W1 component. Okay, that's kind of what we're doing there. Okay. So I guess before we get into the idea of like a formula for projection, let's actually look at example 1, okay? And let's show that U is made up of orthogonal components W1 and W2, which are vector components. So remember, W1 is always going to be parallel to or a scalar multiple of vector V. Okay. And sometimes, even though we talk about W1 first, it's easier for us to visually draw W2. So W2 is always perpendicular to V, and therefore it's also perpendicular to W1. Okay. And so essentially what we're going to do is we're going to take this u value, this u vector, and we're going to kind of project it onto V, where part of it is going to be that projection, and then the other part is the perpendicular to that. Remember that we said that W1 was a scalar multiple of V. That means that we're not limited by this vector V. Oftentimes, sometimes I find it helpful for me to kind of extend it before I draw a vertical, okay? And again, usually our focus is usually W1, but personally, visually, I usually think about taking the tip of U, okay, or end of U, and in this case, dropping that perpendicular here. Okay, so I have this perpendicular. Now I'm not putting an arrow on it yet because I want to make sure that the vectors add appropriately. So what I can do then is complete the triangle. Here's the hypotenuse, and then vectors W1 and W2 make up the right angles. Okay, make up the legs that form the right angle. So I can see here that this part would be W1. I'm going to start at the beginning of U and go here to make W1. Then I would continue where W1 stopped and go up here to W2. And essentially that's what makes that vector U, W1 plus W2. So we're showing that they have these orthogonal components. Again, orthogonal meaning that they're perpendicular to each other, okay? Now that's the most common thing that we're going to be dealing with, to be honest with you, especially in the application problems. But it does say that W1 can be parallel to V. So what I'd like us to do, and for me to make parallel lines, I need them to be kind of longer. See, look at this, okay. And I'm going to think about the line that's parallel to V that goes through this end of U. Do those kind of look parallel? Okay. So, so let's say that we've kind of like moved this idea of the vector V over here. And let's make W1 on this vector that is parallel to vector V. Now in the other one, what I did is I went from the end of U and dropped the perpendicular to V this way. When you're doing it parallel, I'm going to go where U begins, and this is where I'm going to make my vertical, or sorry, my perpendicular line segment, okay. Okay, so that's going to be that piece, and then this will be the other piece right here. And so if I'm looking at those directions, I can see that this would be the W2, and I'm going to start here and go to this piece, and then I would follow through to this piece, okay? And you might say, well, how does that work? This is W2 plus, I should label this W1, okay? Well, they're going to end up being the same. So like if I ended up doing this the other way, like I had done in the past, like in the other one, if I had gone this way and then finished off the triangle this way, I can see that I would start here, and this is going to be my W1. You can see that that has the same direction and magnitude as the other W1. And then I'd finish off this way, and this would be like the W2 vector. Again, the same direction and magnitude there. So you've probably seen in some of the other kind of visual pictures that like you could kind of connect all these to make a parallelogram. But I just wanted to show you about how you could do that with a parallel line to V. Okay. Lastly, we have vector V that's going this way, and we have this vector U. And so let's just put this one back onto U right onto V again. So it's that scalar multiple. So I'm going to take the end of U, and I'm going to try to make a perpendicular line with V. Okay. And so then I would finish off the triangle here. Okay. Then when I think about vector U started here. So I'm going to start with where U started and have that be my W1. And then where W1 ended, I'll make my W2. And again, that W1 plus W2 are orthogonal vectors, making perpendicular to each other, and together that would make up U, okay? Notice W1 and W2 in this case, they're not horizontal or vertical, right? But they do make those right angles. Okay, so that's kind of a visual piece here, all right? So we've looked at that visually, but let's say that we wanted to be a little more specific. Well, there is a way that we can find that. This W1, again, so that W1 is that projection of U onto V. And this is how that looks, okay? W1 is the projection of U onto V. Notice this is not read V onto U, it's the projection of U onto V. Okay, that took me a while, that's why I'm emphasizing that. And here's a little formula that they have for us, that the projection of U onto V, which is going to be W1, is going to be equal to U dot V over the magnitude of V squared. U dot V, the dot product is a scalar, magnitude is a scalar, so this is going to be a specific scalar, and then times this vector V, times our vector, okay? And that makes sense. What we said is we said that W1 is a scalar multiple of V. And that's what this is here. W1 is some scalar times the vector V. Okay? But this is the formula that we're going to use for that projection. Okay? So before we get into the story problems, let's look at an example just so we can practice this formula. Example 2 wants me to find the projection of U onto V. And again, this projection of U onto V is going to be that W1. And it wants the vector component of U that's orthogonal to V. And that's the W2. Okay. So let's start by drawing U and V. So our U is at 3, -5. There's my U. My vector V is going to be at 6, 2. There's my vector V. And I know we've been doing this visually, but let's do it algebraically first, and then we can do it visually and kind of compare to what we have, okay? The first thing it's asking us for is W1. And so we know that W1 is going to represent the projection of U onto V. The formula for that is we're going to take the scalar U dot V and divide it by the magnitude of V squared. And then we're going to multiply that by vector V. Okay, so I sometimes like to kind of do everything kind of separate over here. So like I might down here say, all right, so let me find my U dot V. Remember, to find my U dot V, I'm going to multiply the horizontal components together. So 3 times 6. And then I'm going to add the vertical components multiplied together, 5 times 2. And I don't necessarily need to see that work. So I have 18 plus -10, which is 8. Now I'm also just going to take a quick minute to find the magnitude of V squared. And we know to find the magnitude of V, we take the components and square each one. So 36, 4, and we're going to add them together. But notice we're squaring the magnitude, which means we're going to cancel out the square root and the square. So this just ends up being 40. Okay. So now I can put these back up into this formula. We said that U dot V was 8, and the magnitude of V squared was 40, and then we have this vector V 6, 2. Okay. Well, 8 over 40 will simplify to 1/5. And then we can apply that scalar to the other components. So our W1 is going to be 6/5 2/5. And so that's how we can algebraically find that projection of u onto v. Hang on for the visual, okay? So that's the first thing. Okay. Well, the second thing it then asked us was to find our W2. Well, remember that what we were trying to do is we were trying to break u down into two different vectors. Remember these orthogonal components. Remember we were saying that u, that vector u, is going to be made up of two orthogonal components, W1 and W2. Well, in step 2, it's asking me to find vector W2. And what's convenient is that I know vector u, because that was given, and I just found vector W1. So I can say that to find W2, I can take u minus W1. So let's take a look and do that. My u is going to be 3, -5, minus my W1 I just found was 6/5, 2/5. And so then I might want to make common denominators. So that's going to be with a 5. So 3 is the same as 15/5. -5 is the same as -25/5. And then minus 6/5, 2/5. So I can simplify that pretty easily. 15/5 minus 6/5 is 9/5. And -25/5 minus 2/5 is -27/5. And there's my W2. Okay? Now, let's go back to that visual thinking that we were doing before, and let's see if we can draw the projection of u onto v. Okay? Again, I find it easier to start with W2, so I take the tip of the end of u and I try to make a right angle with that vector v. I probably need a bigger graph, sorry. And then I complete the triangle with this part here, okay? So that little tiny part here, which if u starts here, I would go this way. This would be my W1. And then I would continue this way, and this would be my W2. Now, again, it's hard to see because the grid is so tiny, but remember, we said that W1 was supposed to be at 6/5, 2/5. So that's like 1 1/5, 2/5. Isn't that where this vector is? Like 1 1/5, 2/5. See, that's where it is. That's where W1 is. So that's how we can find it algebraically. W2 is 9/5, -27/5. But remember, like this isn't in standard position. We'd have to like move this vector over. And if we did that from here, we would see that that would match up pretty well as well. Okay, so that's kind of the combination of the visual with the algebraic. All right. So now I want us to talk about, so we've used the formula kind of algebraically, but now let's talk about how that's going to work in an application. Okay. In this boat example, in the boat that is on this ramp, what we are actually going to do is we're going to project the force F onto the ramp. And the ramp is going to be our V, okay? And oftentimes it asks us to find this W1. And so what we can say is that this vector W1 is going to be the projection of F onto V, okay? That's really what that's looking at. It's the projection of F onto V, where V is the ramp, okay? So let's take a look at that and use the algebraic properties to kind of help us out. So in example 3, it says, find the force required to keep a 2,500-pound vehicle from rolling down a ramp inclined 15 degrees from the horizontal. Assume the only force to overcome is gravity. Then we'll find the force perpendicular to the hill. But let's just start with this letter A first. A picture is going to be something that's pretty important Because it's inclined from a horizontal, I'm just going to draw a random horizontal line. Okay. And now I'm going to draw the ramp that's 15 degrees from the horizontal. I honestly don't care how long this ramp is. We'll talk about that why in a little bit. I just care that this is 15 degrees. And again, I'm suggesting that we call the ramp vector V. Okay? So we have this ramp, and on this ramp, there's sitting a vehicle. Okay. So it's a really pretty vehicle. And it has it's 2,500 pounds. So what's happening is gravity is acting on this so that we are going straight down, and I'm going to call this the F vector, vector F. And I usually extend it past that horizontal just so that my triangle is not super tiny. But anyway, we know that this is going to have a force of 2,500 pounds. Okay. And our goal is going to be, again, to decompose that vector F into two different components. So before I would start at like the end of U and go to V, so like this force is our new U, is like the vector that we're really concerned with. So I'm going to start from here and try to draw a perpendicular to the ramp. Didn't do a great job. Okay, but that's going to be my W2, and then the other part that's here is going to be my W1. And if I start at where F began, my W1 is going to be going this way, and then my W2 would be going this way, okay? So that's one of the things that talking to other teachers is important, having that visual, looking at breaking F into those orthogonal components. Okay, so then when we think about it, what's going to happen is that we're looking for the force required to keep the 2,500 pound vehicle from rolling down the ramp. Do you guys see that it's W1 that is the part of the force that's rolling down the ramp? So that's really kind of what we're looking for here. We're going to use W1 to help us with that, okay? Now, the thing is that we have vectors that we know, okay? The vectors that we know are the ramp vector and the force vector. So again, our vector V is really that ramp vector. And I don't care how long V is. I don't. Remember that if we're looking for W1, W1 is a scalar multiple of V. So I don't care if V is 8 million units long or if it's like half a unit long. I don't care because W1 is just going to basically be like a stretch or shrink of that. So a really convenient vector to use would be our unit vector. We could just use cosine 15 degrees, sine of 15 degrees, okay? And that's what I'm going to suggest that you do for these ramp problems. That for the ramp, just use the unit vector, okay? Because again, that length doesn't matter. All we care about is that direction, and then W1 is going to be a scalar multiple of that. So we don't really care what it is. Okay, so then the other thing we knew was F, the force. And we can tell what those components are going to be. We're not moving left or right at all, so the horizontal component is 0. And the force that's going downward means that the vertical component would be negative 2,500. Okay? So we are going to need to use this W1 to help. Okay? So this W1, again, is going to be the projection of F onto V, the ramp. And the formula then that we'll use is to find our scalar. We're going to take F dot V over the magnitude of V squared times that vector V. Okay. So again, I think it might be nice to do some of those to the side. So if I'm thinking about this here, if I'm doing f dot v, then I'm taking 0 times the cosine of 15 degrees plus negative 2500 times the sine of 15 degrees. Okay, I can see this is going to be 0. And so f dot v is just negative 2500 times the sine of 15 degrees. Okay. Now let's find the magnitude of v squared. Okay. Well, guess what, guys? What did we say that v was? We made v a unit vector. Since we made v a unit vector, what's the magnitude of v? That's right, friends. It's 1. And when we square 1, what do we get? We get 1. And so that means that this scalar is going to be this negative 2500 sine of 15 over 1, or just negative 2500 sine of 15 degrees. And then, oops, and then I'll just multiply that because I'm out of room by v. Okay? So what that means is that my W1 is going to be negative 2500 sine of 15 degrees times my vector v. Cosine of 15 degrees, sine of 15 degrees. Okay? Now the thing is that it wanted the force required to keep the vehicle from rolling down the hill. So this is the vector, so it gives us, you know, the appropriate direction that it's going to go with once we apply that to the components. But we're really looking for the magnitude. That's really going to tell us what that is. Now remember that this is a unit vector right here. And one of the things we mentioned is that we can look here for our magnitude, okay? But that magnitude, notice, like has a direction with it as well. So all we're going to do is we're going to find the magnitude, but ignore the sign. So we're going to say that that is this negative 2500 times the sine of 15 degrees. So we could think about like taking the absolute value of that. And so if I take negative 2500, am I in the right mode yet? Times the sine of 15, I get negative 647.04. So that means that that is going to be 647, oh, let's round appropriately, 0.05. And then we're going to keep that unit of pounds. And that's going to be our magnitude of W1, which means that that's going to be the force required to keep the vehicle from rolling down the ramp. Okay? Now the last thing it says, letter B says, find the force perpendicular to the hill. Well, perpendicular to the hill means that that's going to be that orthogonal vector, W2. And one of the things that we noticed is that W2 we can find by taking F minus W1. Now, when I was doing this before with some kids, we were having some trouble. So I'm going to try to write everything out for the video notes so I don't lose too many of you. So I want to take vector F, which is 0, negative 2500. And then I need to subtract vector W. Now the way that vector W is written right now is it has like the this magnitude on the outside and then this piece here. Remember that this can be applied to each of the components. So if I, apply this to the first component, that ends up being negative 2500 sine 15 degrees cosine 15 degrees. And then the second component, we multiply this by the second component to get negative 2500 sine of 15 degrees sine of 15 degrees. Okay? And we're going to subtract those. Okay? So the first thing that I'm going to subtract is I'm going to subtract 0 minus negative 2,500 sine 15 cosine of 15 degrees. And again, I'm subtracting those, so I'm really like adding them, but I'll write the negative here. So I'm going to take 0 minus, and then I'm going to have negative 2,500 sine of 15 degrees cosine of 15 degrees. And that gives me 625. So that's not too bad. Okay. Now I'm going to take negative 2,500 and subtract this vertical component. So I'm going to take negative 2,500 minus negative 2,500 sine 15 degrees sine 15 degrees. This one isn't quite as cute. It's negative 2,332.53. And so I guess because I rounded, I should say that this is approximately equal to that W2, okay? But once again, what we wanted is we wanted the force. So we're going to have to find the magnitude. And we can just use these values. I don't need to see the work for that. We know that to find the magnitude, we're going to take 625 squared plus negative 2,332.53 squared, and then take the square root of that. So that ends up being 2,414.81-ish. And again, that's in pounds. Okay. Usually we stop at what W1 is, but we're just kind of trying to drive home the point that that it's W1 and W2 that make up that vector F, okay? Now, the nice thing about these problems is that once you've done one, like once you've absorbed that, they're all going to be a piece of cake. Let's look at example 4. It says a 600-pound boat sits on a ramp inclined at 25 degrees. What force is required to keep the boat from rolling down the ramp? Well, this one's super nice because all we have to do is find our W1. But we'll start everything the same way. I have my rando horizontal. And now I'm going to draw my ramp, okay? And so this is my ramp vector V. And we know that that has an incline of 25 degrees. This time we have a boat. And that boat has 600 pounds. So here's my vector F. That's going to go straight down because of gravity. And that's 600 pounds. Right? We're going to break that vector F down into 2 orthogonal components. So one of them is going to be perpendicular to V. And then the other one is going to be a scalar multiple of V. That's also perpendicular to W2. So if I think about that, this piece has to be my W1. And now this direction has to be my W2. And there we have our picture, okay? The second thing we wanted to do was make our different vectors. And so our vector, again, this time is vector V, which is the ramp vector. We said we're going to make that a unit vector. So here we're just going to make that cosine of 25 degrees, sine of 25 degrees, okay? And then my vector F, again, because it's just gravity that's acting down on it, there is no horizontal, well, the horizontal component is 0, and then the vertical component would be negative 600. So then we can find W1, which we said that W1 is the projection of F onto vector V. And to find that, we take F dot V over the magnitude of V squared times our vector V. Okay. So we can find F dot V by multiplying the horizontal components together. and adding the product of the vertical components together. Okay. Again, here we end up with 0 and then plus negative 600 sine of 25 degrees. So that's going to be my F dot V. And guess what our magnitude squared is going to be? Lucky for us, we used a unit vector, so that's just going to be 1. Okay. So essentially, what I'm going to have here to find W1, and I can use more room here since that's all I'm finding, is I'm going to take negative 600 sine of 25 degrees over 1, or just negative 600 times the sine of 25 degrees. And then I'm going to multiply that by vector V, cosine 25 degrees, sine of 25 degrees. Okay. If it helps you, again, for this case, you could, you know, kind of like we did up there, is you could make a whole vector and then find the magnitude that way. But again, the beauty is that this is going to be our unit vector. And this represents kind of like the magnitude with the direction. So what we're going to do for this, magnitude of W1 is we're just going to take this and ignore the sign. So let's say that I took, you can even not just type in the negative, but I'm going to take negative 600 times the sine of 25 degrees. And again, we're going to ignore the sign. So that gives me 253.57. And then that's going to be pounds. So you guys can see that these mirror each other. You know what I mean? Like they're very similar. Like once you do one of these ramp problems, you kind of get the gist of it. So see if you can practice some. And I have an extra practice worksheet for you guys as well. Okay. Again, if we wanted to find W2, we could take F minus W1, find that, and then find the magnitude to see what the force perpendicular to the hill would be. But usually we stop here. Okay. All right. Lastly, we are going to be talking about work, okay? When we talk about work, work is a scalar, okay? Which means it's going to be a numerical value. The work W done by a constant force F acting along the line of motion of an object is, so here's W, that's work. We're just going to multiply the magnitude of the force times the distance. So that's what we have here, the magnitude of the force times the distance that we're moving it. So PQ is like where we're putting it, okay? So this is when force acts right along the line of motion. So for example, let's say that you lift a 35-pound bag of dog food up 3 feet. So that means you have this thing that's 35 pounds and you're moving it up 3 feet, okay? That means your work is your magnitude of the force, which is 35 pounds, times the distance that you're moving it, which is 3 feet, and you multiply those together, and that will give you 105, and then the unit ends up being something called foot-pounds. I know that sounds a little weird, okay? Okay, well now let's say instead of lifting a bag of dog food up 3 feet, let's say that we take that 35-pound bag of dog food and we move it 3 feet across the floor instead. As far as our work is concerned, we're still going to take the force, which is 35 pounds, multiply it by the distance I'm moving it, 3 feet, and we see that that work would be, once again, 105 foot-pounds, okay? So notice that these are the same. I have done the same amount of work, okay? Now let's say that the force is not along the line of motion. In that case, then we need to find the component of the force that is along the line of motion. And for that, what we can do is look at that projection of this vector F that's a certain angle away from the PQ that we're dealing with, and we're going to project it onto PQ, okay? So I want us to look at the picture real quick. If I look at this picture, I have a right triangle that exists here, okay? And I have the adjacent and I have the hypotenuse. And that means that I can use the cosine of theta. So the cosine of theta would be this projection of F onto vector PQ. And then the hypotenuse would just be F, okay? Now the thing is that these are distances, right? When we're talking about how that's concerned. So we're really going to take the magnitude of each of those. And so when we look at the projection, so let's say I wanted to write an expression for the projection of F onto PQ, I could manipulate this equation around and say that this is going to be the same as the cosine of theta times the magnitude of F. Okay. So what this means is that this just helps us get some of these different formulas. The work W done by a constant force F acting at a specific angle theta with PQ is given by the following. This right here, the projection of F onto PQ, that times the magnitude of PQ, this is really like the projection form. Okay. The projection form can then kind of like, I don't want to say turn into, but like what we can do is take this projection of F onto PQ. We know that the magnitude of the projection of F onto PQ is going to be the same as the cosine of theta times the magnitude of F. And this is really a helpful form. And so when I often think of this, I'll usually have the cosine of theta, which is the direction I'm dealing with, and then the magnitude is going to be basically the force, and then the magnitude of PQ is going to be like our distance, okay? This is often the most helpful, like in our story problems and stuff like that. Okay. And then there's another way that we can write it, and this is using the dot product. You could also find the work by using the dot product. And so this is the dot product form. Okay. This is also like a projection form, but again, we just turn the projection into something a little more palatable, I guess. Okay. I did say I'd mentioned something about the units of work. One example that we had above was foot-pounds. Another that you might see is this N-M, and this represents a Newton meter. And the Newton meter is the same as a joule, if you've seen that in science class. Okay. But let's look at how we can use these different work formulas. We can say that, let's say a tractor pulls a log 800 meters. The tension in the cable connecting the tractor and the log is 1,600 kilograms, or 15,691 newtons. Approximate the work done if the direction of the force is 35 degrees above the horizontal. Well, do you see that they give us an angle measurement? That means that the most helpful work formula is going to be this guy right here. What we're going to do is we're going to take the cosine of theta times the force times the distance. And all that information is there. So let's take a look. We know that our theta in this question is going to be that 35 degrees. The force is going to be that amount in kilograms or newtons. Well, notice they tell us meters here, and Newton meter is a nice unit of work. So let's use the 15,691 newtons. And then it tells us the distance that it moves. It moves 800 meters. And then, my friends, we're just going to multiply those together. We're just going to take the cosine of 35 times 15,691 times 800. And yes, that's how big this is. So what we're going to say is our work, I'll put it down here, is 1028261.78. So putting the commas in, it's going to be 10,282,651.78. And then my unit would be Newton meters. That's it, okay? So these aren't really that bad. Okay. Example 6 says to close a barn's sliding door, a person pulls on a rope with a constant force of 50 pounds at a constant angle of 60 degrees as shown. Find the work done in moving the door 12 feet to its closed position. Don't we have all this stuff again? So all we need to do here is take the cosine of theta times the force times the distance that we're moving it. So we can see here that my theta is 60 degrees. The constant force is going to be 50 pounds. And we're moving it a distance of 12 feet. So we're just going to take the cosine of 60, which we know is 1/2, times 50 times 12. We multiply that together. That's going to give us 300. And the unit here is going to be foot-pounds. Okay. I know I'm running out of time. I'm glad you guys listened to this at 1.5 speed. I do want to do a little FYI because there are sometimes like some problems that are not application problems where they might want you to use the dot product form to find the force. So if I'm looking at the different vectors that I have here, if I look at this force vector, again, I'm going to have that force of 50 pounds, and then I'm going to have the cosine of 60 degrees, sine of 60 degrees. And again, I could apply that to each one to get the force vector. But that's my magnitude, and then that's the direction angle. Okay. Then I have PQ, and PQ, notice, is going from here to here. So it's moving over to the right 12, but it's not having any vertical component this time. Okay. So again, another way that we can find work is by finding the dot product of F and PQ. So we can say that the work is going to be F dot PQ. And we know that that would be 50 times the cosine of 60 degrees times 12 plus 50 times the sine of 60 degrees times 0. So again, this just ends up being 0. And so then we would just take 50 times the cosine of 60 degrees times 12. Oh, isn't that what we have here? 50 times the cosine of 60 degrees times 12. Do you see how they end up being the same thing? So again, we get that our work is going to be 300 foot-pounds, okay? And notice that that's the same. Okay. So if there's a non-application problem, then sometimes that dot product form is nice to use. Okay, and then last example is real similar to what we had just done there. It says a mover exerts a horizontal force of 30 pounds on a crate as it is pushed up a ramp that's 20 feet long and inclined at an angle of 15 degrees above the horizontal. Find the work done. Let's use this little buddy. Let's use the cosine of theta times the force times the distance. Okay, this time you guys can see our theta is 15 degrees. What would the force be? That's right, 30 pounds. And what's the distance we're moving it? 20 feet. So I would just take the cosine of 15 times 30 times 20, and that gives me about, that my work is going to be about 579.56, and then again, that's in foot-pounds, okay? And then again, that is the work that's done, okay? So that's a little bit about work. Thanks for hanging out, and sorry I went a little over, but hopefully you listened to it faster, okay? That's it. You guys have a great day.